Unit 8, practice problem number 58. That's a lot of 8s. Okay, so we've got some object, who knows what it is, and it has a force position graph as shown in this figure down here, this kind of weird triangular looking thing. The object is starting from rest, so its initial velocity is 0 at a position of 0, okay? What we'd like to know is how much work is done on the object as it moves from x equals 0 to x equals 2 meters for part A. So as it goes from 0 out to 2, how much work is done? And then for part B, how much work is done as it goes from position 2 meters to 3 meters? And then last but not least, what we'd like to know is what's the mass of the object if out here at 3 meters we have a final velocity of 2.3 meters per second. So this looks like, once again, one of our work energy problems here, but because we're given a nice graph here for a non-uniform force, let's go and find ourselves some areas. Let's start for part A here, and in part A, we were just asked to find the amount of work done from 0 to 2 meters. And remember, work on a graph like this is nothing more than the area. So we're really trying to find the area throughout here, which is a kind of weird and funky shape, but you can break this up in many, many different ways, however you like to. We're going to pause this video here. I'd like you to try to break up this weird-looking shape into some easier, smaller shapes, and then try to find the entire area of that region. So let's dive into this. I see here, like I said, 2 triangles and a rectangle. So my first triangle I see is like this here, across, and then up. Since this is a nice right triangle, we can use 1/2 base times height here. So 1/2, the base, as my computer goes nuts, is 1.4, because this is 0.2, 0.4. Where was I? Okay, so there's 1, and then so it's 1.2 and 1.4, because 1.6, 1.8, and then 2. And my computer's going nuts. So this base here is 1.4. And then my height here goes from 0 all the way up to this tippy top of 0.8. So that's going to be 0.8 here. So multiply that together, 1.4 times 0.8 times 1/2 gives me an area of this triangle of 0.56. Another triangle I see is up here. This is also a right triangle, so I can use 1/2 base times height. My base here is 0.2, 0.4, 0.6, and my height is 0.1, 0.2. My height is not 0.8. My height is 0.2 because I'm going from 0.6 to 0.8, and that's only a difference of 0.2. So 0.6 times 0.2 times 1/2 is 0.06 for this area. And then the last thing I see here is this wonderful rectangle that's been created by the rest of my edges. It has just a length and a width to it. So the width is 0.2, 0.4, 0.6, and the height goes up to 0.6 as well. 0.6 times 0.6 is 0.36. So when I add these three values together, 0.56 plus 0.36 plus 0.06, we get a total area in part A of 0.98. And technically, that's in joules. This also means that if you're actually looking at my note sheets, the answer is wrong on that. Old little teacher trick, put a wrong answer, see who actually does the problem. Anyway, in part B, we'd like to know how much work is done for the second part, from 2 meters to 3 meters. So we have a slightly different area here. And if you're looking at this, maybe you remember a trapezoid equation. I certainly don't, but if you do, you can absolutely find the area doing that. What I'm going to do here is I'm going to split this into a nice rectangle here, or a square, however you want to think about it, and then this triangle up top. So for my rectangle down below, it has a base equal to 1 because I'm going from 2 to 3, so that's a distance of 1 there. And then my vertical height of it is 0.3 up here, so this height here is actually 0.3. 1 times 0.3 is 0.3. So that's my area of just the rectangle. If I take a look at my box, or rather my triangle up above, I can do this in 2 ways. I can do the 1/2 base times height. There's nothing wrong there. My base would be 1 again. My height would be 0.3, and I take half of that. I can also recognize that if I completed this, I get the same box as down below, but then I cut it in half, which means my area up top is 0.15, or 0.3 divided by 2. Which means my work for part B is 0.3 plus 0.15, or 0.45 joules. So we found works just by calculating areas, however you wanted to break those shapes up, whatever equations you wanted to use for trapezoids, triangles, squares, however you wanted to do it, that is up to you. I showed you how I saw it, but if you see it slightly different, there's nothing wrong with that, okay? Now in part C, we start getting back into a little bit more of the work energy idea. We've just been looking at works and areas, but for our work energy idea, we want to know what's the mass of the object if at the end it's moving at 2.3 meters per second. So what we can do here is we can remember that work equals a change in kinetic energy, or that the total work equals some 1/2 multiplied by a mass multiplied by a final velocity squared minus an initial. Or a final velocity was 2.3 squared minus the initial of rest, which is 0 squared, so really we don't even have to write this in. We can just kind of whoop, 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 get rid of it from the equation. But on our left side here, which was normally fx cosine theta, this is just this work, which we know is the area. But remember, since we're going from 0 meters to 3 meters, we want the total work done. We actually want all of this area, which is fine because we found it in pieces. We found it as 0.98 and 0.45. So if we just add the 0.98 and 0.45 up, 0.98 plus 0.45 gives us 1.43. This equation right here is now easily solved for m. We can multiply each side by 2. So we're now going to get 2.86 equals m times 2.3 squared. If you want to square the 2.3 and then divide it, or divide it by the 2.3 squared, it doesn't really matter. Let's square it first. So 2.3 squared is 5.29. So let's just rewrite this. 2.86 equals m times 5.29. And then we simply divide by the 5.29. 2.86 divided by 5.29 gives us a final mass of 0.54, and because we're in SI units, this must be in kilograms. So not too crazy of a problem there. Just like what we've seen previously, these work energies, we are just using the same equation here. Some work equals 1/2 m vf squared minus vi squared. Recognizing, though, that in our case, when we're given a non-uniform work, and we have a graph here, that work is just equal to the area, and that just means we're taking a look at the graph, saying what kind of triangles, squares, rectangles, what weird shapes can we make to find that area, and then let's use that area in our equation, okay? So nothing crazy there. We've done a bunch of problems like this thus far. The only addition on what we've just seen is that area, and that's something we can definitely do, and we've actually done in prior units. So with this problem is finished. At this point, what we'll be looking at in following videos is, instead of looking at kinetic energies, we're going to be looking at how we can store energy to get it back later. So until next time, hope you enjoyed this. Adios, and take it easy.